Welcome back. We talked in the first part about what translation is and the mathematical perspective into what translation is, as well as what machine translation is. In particular, we focus on the modern way of building a machine translation system or modern paradigm called neural machine translation. And we spent quite some time trying to go over the basics, and then we in fact jumped into talking about two fundamental issues of the current paradigm that is based on statistical estimation for machine translation. And then those two fundamental issues, as we discussed earlier, are somewhat unavoidable just due to the fundamental limitations given to us as a part of the definition of the problem. And in fact, one of the most important limitations is that we somehow have to assume, or maybe we just have assumed, that the source sentence that we are given with is complete, and that there is no ambiguity in terms of how the source should be and could be translated. Unfortunately, it turned out it's very difficult to determine whether that is the case to start with. And even if we know that this is almost never the case, it's not really easy to come up with a controllable way for us to see and decide as a user which of the possible translations are more plausible than not. So these two issues that are very highly related with each other turned out to be the things that we cannot really easily tackle within this problem setup that we have been using for machine translation. And perhaps it's time for us to really think hard about the problem itself and what is the right way to formulate this problem so as to make machine translation much closer to how humans, professional translators, translate. Unfortunately, I really don't have any answer to what is the right way to go about. Now, that said, it actually does not mean that there are only those fundamental issues that cannot really be addressed within the current paradigm or current dominant paradigm of machine translation. In fact, the current paradigm of machine translation, which heavily relies on autoregressive modeling, has so many weird degeneracies that have both been identified and are still unknown that we need to fix in order to even use the current paradigm of machine translation as well as we can. Now, during the past few years, I've been trying to identify and tackle some of these degeneracies. And sometimes I've been successful, some other times I haven't been successful. And then today, in this second part of the lecture, I'd like to share one recent case of degeneracy that together with my PhD student who is graduating now, Ilya Kulikov, and master students Maxim Eremev at the NYU Center for Data Science, were able to characterize quite reasonably. And then based on the characterization, we could come up with some, reasonable, not perfect, reasonable way to address this issue. And then that issue is oversmoothing. Let's see how we characterize it, and then what this degeneracy is according to our characterization, and then how we actually tackled it. Now, unfortunately, it turned out that we only tackled some part of this issue, and then the issue in general still exists, and then we're going to talk about what are the remaining mysteries or the degeneracies, and then how I believe we should actually move forward in order to tackle the remaining mysteries. So we will stick to language modeling. The reason why we stick to language modeling rather than machine translation, which is a special case of conditional language modeling, is just because we don't necessarily care that much about what kind of source information we condition our language model on. In the case of machine translation, the source was a source language or the text written in source language. But we could very well use the very same paradigm for, say, image caption generation where the source is going to be an image. We could have the video description generator where the source can be some features generated or extracted from a short video clips. Well, if you're working on, let's say, summarization, then the source is going to be a much longer text. If you work on the question answering source, it's going to be a question often attached together with some context from which the answer could be selected. So we don't really care. What we're going to talk about is on the decoding side, that is on the target side. Now, just like before, let's actually go over the details once more because the details actually turned out to matter quite a bit when we think about all these degeneracies or the issues in these neural autoregressive models. So the setup is that we have a sequence of discrete tokens, and then each and every one of these discrete tokens comes from a finite set of all unique tokens V. The length L of such sequence will vary from one sequence to another. And that's what makes the sequence modeling very, very interesting because what we have is some object whose size even changes, and then it's only natural that it happens. And then the size does not tell us only about the resolution at which the information is present, but the length itself, in fact, does tell us a lot about the information. Now, one thing that I did not emphasize earlier in the first part, but this part is extremely important, is that every valid sequence Y ends with a special symbol EOS, which stands for end of sequence. So any valid sequence Y is going to have end of sequence token at the very end. If I see a sequence that doesn't have the end of sequence symbol at the end, that is not a valid sequence. If I see a sequence where end of sequence token, EOS token appears in the middle, then it is not a valid sequence, but only the prefix up until that first occurring EOS is a valid sequence. Now, with this in our mind, our goal in language modeling is to build a model, often parameterized by a finite number of parameter theta, that computes a probability P of Y a sequence given under this model that is parameterized by theta. And of course, we want a reasonable sequence Y to receive a high probability under this distribution. Language modeling is fascinating. That's why everyone is going crazy about this so-called large-scale pre-trained language models. Why is it fascinating? I thought this is a fun thing to talk about before we talk about some issues with these language models. And in my opinion, the reason why it's fascinating is just because natural language is a fascinating way to encapsulate ideas. Really, if you imagine how you convey any ideas that you have to others, you use language. And then that's fascinating. Those ideas are sometimes extremely concrete, talking about a very specific stuff. For instance, I can describe what this is, my phone is, using natural language. It's a very concrete concept. But at the same time, I can talk about, let's say, politics, like the democracy, love, hate, all these abstract notions or the abstract concepts using natural language as well. It's really amazing. We have this one communication protocol that allows us to describe all these concepts, all this diverse set of concepts that are both extremely high level as well as extremely low level. And what this allows us to do is to encode many different problems in this single protocol that is natural language. We can encode the problem of extracting the relationship. Who is Barack Obama to the United States? The answer can be given in natural language as Barack Obama was the 44th president of the United States. We can encode the common sense reasoning problem. Jane performed an emergency surgery on John because, and why did she do so on John? And then our answer could very well be because John was in a car accident. question answering is very, very natural language processing problem. What is Wikipedia? Wikipedia is a free content, multilingual online encyclopedia written and maintained by a community of volunteers through a model of open collaboration. Even translation, in fact, can be simply described in natural language. What is 뉴욕대학교는 뉴욕시에 위치한 사립대학교이다? In English, the answer is New York University is a private university located in New York City. Language is fascinating, and thereby our attempt at building a language model is also fascinating. Now, thinking about, considering all those examples that we just talked about, what we realize is that all these problems can be solved by solving this one optimization problem. That is, given a language model key, so that is, we have the theta, right? We observe some of the words, but then we are missing some of the words as well. Now the question is, what is a way to infill or to complete these missing words so as to maximize the log probability assigned to this completed sequence by our language model? Let's go back. Let's think about the relation extraction. What are observed? Barack Obama, the United States. What are missing was the 44th president of. So all those 5 words in the middle. And how do we solve this problem of relation extraction? We're going to try all possible way to fill in this missing center of a sentence that starts with the Barack Obama and ends with the United States. And we ask the language model which possible completion is most likely. And then according to the language model, we'll choose this 5 particular word sequence that is, was the 44th president of. And then that actually tells us about the relationship between Barack Obama and the United States. So yes, language is fascinating because it allows us to encapsulate ideas, and language modeling is fascinating because that allows us to allows us to search for the most plausible ideas given some context. And then that allows us to solve so many different problems using a single model. That's pretty awesome. And as we talked about in the first part of the lecture, we are going to stick to autoregressive language modeling because it actually turned out it has a very nice properties. And then that property is that it can handle sequences of varying length very naturally. And it's also compositional, although it's quite simple one, but still compositional. And how does it do that? Is by having, in fact, a single classifier rather than a complicated language model. We write the probability of a sequence of discrete tokens as a product of the probability of each and every one of those tokens given all the preceding tokens within the sequence. So what that means is that all we need to know is how to compute the conditional probability of the next token or the next word given all the previous words. So this is the gist of the autoregressive language modeling. Now that we're talking about the autoregressive language modeling, why don't we talk a bit about where it actually comes from? Who was the first one who decided to look into this kind of approach? It turned out that already in 1950, Claude Shannon, the father of information theory, in fact, realized that this kind of autoregressive modeling is a really good way to model language. And then the reason why he wanted to model the language was because he wanted to measure the content or the amount of the information encoded in English. And then how he did was to define the notion of statistical or probabilistical entropy, or we call it Shannon entropy, and then trying to measure the entropy of the English distribution, where the distribution of the English was defined in an autoregressive way. Now I have highlighted some of the portion from Claude Shannon's original paper from 1950. And then what you notice is that this is exactly how you define this autoregressive model. And then once you define it, how you compute the Shannon entropy of the model. Now, of course, it was 1950, Claude Shannon tried his best to estimate the number of bits that are encoded or that are needed to encode English at the letter level. But, it's not like Claude Shannon had power of all these powerful digital computers back then. He really literally had to do everything either manually by calculating all those quantities by hands, or had to essentially literally build a computer in some sense, right? Often using the switchboards and whatnot. So this idea has been there, but has been only pursued sporadically by a small number of people throughout the time. But by late 90s, we started to have access to powerful digital computers, and then the idea of using autoregressive model and the power of a complicated neural network to build a powerful language model started to blossom. And then the very kind of, let's say, first modern, let's say, autoregressive language model was proposed by Yosha Benjo and his colleagues in 1999 and 2003. And then there, they built a so-called n-gram language model with a neural network by cutting off the prefix to be of a fixed length, because it wasn't really easy to build a neural net that is able to handle the variable length or variable length input. By another 10 years had passed by 2011, and then spearheaded by Tomasz Mikolov as well as Alex Graves. By then, we knew how to build a recurrent neural network that is able to handle a variable length context, so that we can indeed build a neural network or the neural autoregressive language modeling without any limitation on the context. And then that's when the things got so much more interesting. And then nowadays, starting from about 2018 or so, I started to call it the war of, the number of parameters began. This is a slide, the chart that I took away from one of the Microsoft's blog postings. And then that blog posting is from early last year, I guess, or the spring last year. So it's been less than a year, and somehow it's already outdated. And then if you look at the y-axis, you notice that it's in the log scale in billions of parameters. So the sizes of these models, as well as the sizes of the data used to train these models, are simply increasing exponentially at the moment. Of course, I somehow find it a bit ridiculous that we are grinding so many PhDs on this war of number of parameters. So I'm not going to talk about it too much. But then I want to say that the simply scaling up all these things, which is awesome. It actually brings out all those properties that were not showing up when we were training a very small models on a very small amount of data. But then does not actually resolve all the fundamental issues of autoregressive language modeling. We'll talk about one of them now. Now, let's just think of the autoregressive language modeling, and then what people have been doing, including myself, is to reduce it to text classification. That is, we try to train a neural net that's going to take as the input some variable length sequence that's a prefix y1 to yt-1, as well as there's some context x, but as we talked about it earlier, we're going to ignore it for now. And then we try to map it into a categorical distribution over all possible next words. And then there are only a finite number of them. And then we train this model to put the as high a probability as possible to the correct next word. Now, building this kind of classifier can be done using any of the techniques that have been developed over the past, let's say, 20, 30, 40 years. There are two major paradigms to do so. One is using a recurrent neural network, such as the long short-term memory units, as well as gated recurrent units. And the other way is to use a fully attention-based network such as transformers. The advantage of using a recurrent neural net is that in the forward pass, in the inference time, the memory and computation is constant with respect to the length of the prefix. However, that actually does also imply that it's fairly difficult to train these models, and also the processing is inherently sequential. Now, on the other hand, the attention network, the computation can be highly parallelized in terms of scoring, and then it is also fit for network, making it extremely easy to train. Unfortunately, in the forward pass, in the inference time, the amount of memory as well as the computations grows at least linearly with respect to the length of the prefix. So the memory grows, which was constant in the case of the LSTM and GRU, and then the computation also grows, which is again constant for each of the slice in the sequence in the case of the recurrent network. But again, this is not what I want to talk about it today, but I just wanted to tell you that it's taken many decades, but we've come to a point where we have a parameterization of these deep neural networks. That is how we build them, that allows us to train these very large and very deep models fairly effectively. So then let's talk about how we train this. So we said that we reduce the problem of language model to text classification. What that means is that what we do is we really literally train a classifier. And then how we do so is by minimizing so-called cross entropy. Now, what is cross entropy? If you're familiar with the entropy, entropy is the expected negative log probability under the same distribution. It actually tells us how smooth the distribution is. If the distribution is extremely picky, so everything is all zero, but one of them is one, then the entropy is going to be zero. However, if it's flat, that's going to have the maximal entropy. Now, on the other hand, the cross entropy, so this one is about the one distribution, but now the cross entropy is slightly different. It's the expected negative log probability under a different distribution. So we're going to look at the same the distribution P star, but then we try to look at how well how much probability the other distribution P is going to put on a points that are highly likely under P star. So that's what we're computing. That's the cross entropy. And then what this cross entropy does, or the minimizing cross entropy does, is to estimate the entropy as well as we can. So when we don't know the entropy of the distribution P star, what we can do is we can start by generating samples from this P star that is collecting the data, and then trying to train this language model or the classifier P of y given x by minimizing the cross entropy and all the way down. Because the cross entropy is upper bound of the actual entropy, if we try our best, we can get our best estimate of what the entropy of this P star is going to be. And what that means is that the training this kind of language model, or thereby training this classifier, so next word predictor, is equivalent to finding a distribution that matches the inherent entropy of natural language. Because a language is inherently ambiguous, the entropy is not zero, but some positive value. Now, what we want is that we want to find a distribution that's going to match this true entropy of the natural language as well as we want. But I digressed. I just love this point myself, so I just wanted to bring it up. But anyway, so the cross entropy, obviously we cannot compute it exactly because we don't have access to P star, but we use all the data points we collect, so the corpus that we have, as if there is a sample generated from P star. And because it's an autoregressive model, and then we work at the log domain, everything becomes simply the sum of the log probability of the correct next word given all the previous words within each of the example. Looking at this loss function, we notice that it's almost like training a classifier. It's really just training a classifier. If we assume all these examples are IID, that is like independently drawn from the identical distribution. That's what we talked about in the first part of this lecture. Unfortunately, that is not the case. In fact, given any sequence, given any sentence or the paragraph that you can imagine, all those tokens act as if they are independent examples to train this classifier. However, they are extremely, extremely correlated with each other because they come from the same sentence. The fact that I have said some words in the sentence already tell me a lot about what are going to be the labels for the other tokens or other examples in this classifier learning. That's exactly what we again talked about in the first part of the lecture when we talked about the strong statistical dependencies among the target tokens in machine translation. So in other words, it is indeed almost like training a classifier, but it's not quite. Unfortunately, it turned out no one really cares about this, and then people have been really just ignoring the fact that we are working with many different sequences and simply looking at individual token as if that is the indeed IID example to train a classifier. Let's take a step back a bit. What makes EOS special is that the EOS token always appears exactly once for every training sequence or any kind of valid sequence, and always at the end of the sequence, end of each sequence. Now, let's just assume that the EOS token, the special token, was not there. We just forgot to add it in, which is almost always the case these days when people train all these large-scale language models. Then weird thing happens with this autoregressive model. Given any sequence, let's say y1 to, let's say, capital T, if I take any prefix, any length prefix, so y1 to small t, under this autoregressive language model, the probability assigned to the prefix always more likely, is higher than the probability assigned to the full sequence, although the full sequence is the actual training example. And then why is that? It's just the consequence of using probabilities or consequence of using so-called locally normalized model. Every term that we multiply in order to get the probability of a sequence in autoregressive model is bounded from above by 1. This is really, really weird. So shorter, the better. That's really, really weird. Because in natural language, we know that the short sequences or the short sentences are not necessarily more likely than longer sequences. In fact, when you look at the, let's say, English sentences in news articles, the average length of these sequences are about 23, and the variance is also pretty much finite. What that means is that definitely it's unlikely that the sequences of, let's say, length 1 or 2 are always more likely than the sequences of length, let's say, 20. Doesn't work like that. So what is going on here, right? It turned out that the end of sequence token is not just there to mark the end of sequence, but it actually performs a very special role. It essentially saves us from this weird behavior. As I said, any valid sequence ends with EOS token. Then we can actually make the prefix, so y1 from yt, small t, to be less likely by appending EOS at the end in order to make it into a valid sequence, and then also ensuring that the full sequence ends with the EOS. Now then, although the probability of the prefix or the sequence excluding EOS is always going to be higher than a probability of the longer sequence that contains this prefix excluding EOS. However, by having the probability of the EOS attached to both the shorter as well as the longer sequence, this EOS probability can effectively make the probability of this prefix to be smaller than the probability of the original sequence. It just has to be extremely, extremely small value. Now then the question is, how small should it be? Now, because we are working with the sequences and we're not working with classification, we actually know exactly how small the EOS attached to any prefix of the original sequence be. That is, probability of the EOS after some prefix has to be smaller than equal to the probability of all the suffix, so the following tokens in the original sequence, which is the correct sequence. That is, we have to ensure that the EOS is highly unlikely after a prefix of the original full sequence. And the important thing is not just unlikely, so less likely than the correct following word after the prefix is not enough. The EOS probability has to be highly unlikely. In fact, we know exactly how unlikely it should be. And then that is that it has to be as unlikely as the product of the probabilities of all the suffix tokens in the original sequence. This is the only way, or this is, well, okay, only is always a very strong word, So this is a way for us to ensure that the premature sequence, so that is just a prefix plus a EOS, some random prefix plus EOS, is less probable than the full sequence. And if you think about any natural language sentence, it makes sense. Almost always, if you chop any sentence in the middle randomly, the chance that the premature sequence is not well formed is very high. Full original sentence should be more likely, except for very few exceptional cases. So then now we can define, so this is how we are going to define what we mean by oversmoothing. It's the oversmoothing of the probability assigned to EOS token, in a sense that because the EOS token's probabilities are not dramatically small when they should be, we get this behavior of the oversmoothing that makes this premature prefix or the premature sequences to be highly likely and almost always more likely than the full original sequence. And we define the so-called oversmoothing rate in order to check how often that happens per sequence. So we count how many premature sequences of a full original sequence are more probable than the full sequence by checking this inequality at each and every location, that is, after each and every premature sequence. In natural language, as well as in many applications, what we want is for this oversmoothing rate to be very, very small. However, when we check the machine translation systems that are, more or less state-of-the-art across many different language pairs, we observe that the oversmoothing rate is absurdly high. They were close to 0.5. That is that the half of the premature sequences received higher probabilities than the full correct translations. That's super absurd. That is super duper absurd. Only way in which, in particular, because this is machine translation, that this can happen is one, the data set is completely corrupt, which is not the case because that is the reason why we tried it on all these different data sets and different language pairs. Two is that there are some, let's say, unnecessary, let's say, punctuation marks at the end that can be ignored, and in fact, ignoring them could make the translation more natural. But that's never going to be half of the cases or the premature sequences. So what this actually really tells us is that if we treat the EOS as a normal token, just like all the other words, and then if we don't take into account this nature of the sequence generation or the sequence moving, and then just thinking of it as classification, then there is no reason for our learning algorithm to ensure that the probability of the EOS after a premature prefix is low enough. It's going to be lower than the best or the correct next token, but there's no pressure for our model to put it all the way down. And in other words, we really have to take into account or incorporate this sequence structure, the fact that we are doing the sequence movement. So then, what can we think about? Perhaps we can just minimize the oversmoothing rate directly. Unfortunately, oversmoothing rate is not easy to minimize directly because it is an average of 0,1 losses. In other words, this oversmoothing rate, this function oversmoothing rate is piecewise constant. And the one thing we know is that if we have a loss function that is piecewise constant, we really don't know how to minimize it, other than just trying, all those random configurations and hope that one of the configuration would fall into a piece that's going to have a very low constant value. However, of course, what we've been doing in machine learning is, in particular in classification, is to try to come up with a proxy, often the convex proxy, to a piecewise constant loss function in order to effectively and efficiently minimize it. And then one such way is to use a piecewise linear loss with a margin. So we are now going to minimize the hinge loss with some margin m, so that minimizing this will eventually minimize this 0,1 or the piecewise constant loss. And then what does this oversmoothing loss look like? Is trying to see how much larger this EOS probability assigned to the premature sequence is relative to the log probability of the suffix, which should be in fact larger. So if this one is large, we're going to try to push it down. But then once we push it enough so that there is enough margin between whatever we have pushed and whatever the target, the log probability of suffix was, we're going to stop. That's where this piecewise linear function becomes constant as 0. So this is going to be the oversmoothing loss that we define and in fact explicitly minimize. Now, looking at this oversmoothing loss, there are two major terms. The first one is the log probability of EOS. So what we want is that whenever the EOS shouldn't be there, so after some prefix, we try to ensure that the log probability of EOS goes down even more so than all the other tokens that are incorrect. So if you recall the formulation of softmax and then how the gradient of how the log of the softmax looks like. So the first term in the log of softmax is the log score of the correct token. And then the second term is the log sum of the scores of all the tokens, including both correct and incorrect ones. And then by trying to maximize this quantity, so the log softmax of the correct one, we try to increase the score assigned, probability assigned to the correct one, but then automatically we suppress the probability of all the other tokens. So that's already there, but what the first term in this oversmoothing loss does is to, among all those incorrect tokens, we treat the EOS token even more specially by pushing it down further. And then now the second term is actually telling us that there are two ways to go about. One is to push it further, but also we can increase the log probability of the suffix as well. So we do either one of them, right? And then once we are sure that the incorrect EOS probability is sufficiently lower than the suffix log probability, then this oversmoothing loss disappears. And it turned out that this oversmoothing loss indeed dramatically lowered the oversmoothing rate. So we can really explicitly and directly control the oversmoothing rate and then lower it as much as we can. So the x-axis on this slide corresponds to the weight alpha that we use in order to compute the convex sum between the log likelihood loss, so the usual log likelihood loss, and the oversmoothing loss. So it's going to be the alpha 1 minus alpha times the negative log likelihood loss plus the alpha times the oversmoothing loss. As alpha goes up, we can see that the oversmoothing rate drops quite dramatically from, let's say, all the way to 0.55 down to 0.1. And then that happens across all those different language pairs as well as a different data set as well. So how does it happen? It turned out that the major component in reducing this oversmoothing rate was the first term. That is that the log probability of the EOS at an incorrect location. As you see on the right panel of the slide, the average log probability of EOS in a place where it shouldn't have been, because so that is after only the prefix, not the full sequence, drops quite dramatically. It drops dramatically as in it goes all the way from the minus 15 to minus 100. And don't forget, it's a log probability. One tick corresponds to double the probability. It's a extremely dramatic changes. And it's even more visible if you look at the rank of the EOS. So at each point, we get a probability, we compute a categorical distribution over all possible tokens, including EOS. Now, once we sort it according to probability, we can see how highly ranked the EOS token is. And in particular, when this EOS token shouldn't be at that place. So we want the rank to be low. Now, of course, the rank is like the weird. Rank 1 is the highest rank. Rank, let's say, size of the vocabulary is the lowest rank. But then what we see is that without oversmoothing loss, even though the EOS token shouldn't appear there, the rank is extremely high. But once we actually increase the strength of the oversmoothing loss, the rank of the EOS in the position of the EOS in this rank list drops dramatically all the way to the bottom. So we really ensure that the EOS token is not going to show up in this ranked list when it is not supposed to show up. And this really matters because we know from my earlier work together with the Sean Wellick and also Ilya Kulikov as well, is that at the end of the day, we're going to use some kind of approximate decoding algorithm such as a beam search or greedy search. And then what really matters is the rank rather than the actual probability. The fact that we can lower the rank of the EOS token in the incorrect position all the way down, in fact, already tells us a lot that this approach should work better in general, even in practice. And even more surprisingly, having the very high degree of oversmoothing loss, that is alpha value all the way to 0.95, does not hurt the overall perplexity. That is, how well this language model works as a language model by predicting the next word correctly. What that means is that there are many different ways to perform language modeling. And then all those different solutions eventually end up having a more or less same level of language modeling performance, but some of them suffer from oversmoothing while some others don't. When we did not use the oversmoothing loss, learning always found those solutions that suffer from oversmoothing, but by introducing this oversmoothing loss, we could essentially steer learning towards solutions that still perform at the same level in terms of language modeling, but do not suffer from the issue of oversmoothing. This is a great news. What that means is that indeed, not taking account this sequence structure when training this sequence model was indeed finding some suboptimal solutions, and by introducing a regularization term that explicitly takes into account the sequence structure, we can steer the whole learning towards a solution that suffers less from this particular issue of oversmoothing. Now let's take a quick step back and then see if the oversmoothing actually happens in the wild, just like what we have seen from our own experiments. In fact, already from 2016, Cohen and Knowles reported that there is something weird going on with the neural machine translation. And one thing that they noticed as one of those weird things was the fact that the better search, so we're going to do the beam search, but with an increasingly large beam size, often leads to worse translation. So we're searching for a solution better because we are using a better search algorithm in general. So it's not guaranteed, but in general. But somehow the solutions or the translations that we find tend to be worse. And how they are worse often is due to a shorter translations. So that was a kind of weird thing. But no one really cared because we all thought that, yeah, we're going to use just a small beam size then. And then in 2019, 2 years ago, actually now almost 3 years ago, Felix Stolberg and Bill Byrne show that there is something even weirder happening, or in fact, it's the same issue, but it's more dramatic. What happens under the hood is that when they looked at all these machine translation systems, they noticed that for so many source sentences, the most likely translation under these machine translation models or the conditional language models were the empty strings. So the sequence which has only EOS token, that's still a valid sequence. It's a valid empty sequence because it has just one EOS at the very end. However, there's no other token. And then for instance, with the transformer base, they found that the half of the translations, half of the source sentences, for half of the source sentences, the model preferred empty translations. Super weird. But somehow, again, beam search with a small beam size does not find these crazy empty sequences. That's why we have been able to use these models, and then that's how we actually, all these commercial entities were able to deploy these models. Obviously, there's a reason why we can use it because we've been using these post-hoc fixes. So we've been using so-called length penalty during decoding so that we penalize too shorter sequences. We don't even penalize. Sometimes we kind of block any too short sentences, translations directly. That's a trick that we've been using ever since 2014 with the neural machine translation. And then this is like one of the most important heuristics in neural machine translation. And then those techniques, these heuristics are used in production systems as well. Now we can be a bit more principled and learn how to set the length penalty correctly from data as well. That's what in 2018, Kenton Murray and David Chang proposed is to add a length penalty, but there is a small knob that we can tune based on the data so that the length penalty can be introduced to the degree that's going to maximize or minimize the length difference between the true translation, the correct translation, and generated translation. But still, this doesn't really resolve the issue of why this happens. Indeed, a paper from 2 years ago, Xie et al. Mentioned in their paper that none of these approaches directly solves the mystery. That is, why doesn't maximum likelihood training already shift probability away from empty output candidates toward the appropriate length ones? No, I just told you why, and then how we can actually steer or force the maximum likelihood training to prefer the solutions that suffer less from such an oversmoothing issue. And then that is by defining the oversmoothing very carefully and then characterize it very carefully and then directly and explicitly minimize this issue that is reflected in this oversmoothing rate. So, but does it actually solve the issue of let's call it length degeneracy that Cohen and Knowles in 2016 already observed, and even before that we knew about it, thereby we had to use this ad hoc length penalty in decoding. It turned out that the answer is true. We don't need a length penalty anymore, even with a very large beam search, to get a translations that are of a reasonable length. We could increase the size of the beam to 1,000, but as long as we penalize the oversmoothing loss rate significantly, that is the right side of each of the plot, we could ensure that the length ratio, so the difference ratio between the correct translation over the generated translation, can stay reasonably low, close to 1. We didn't have to use any kind of length penalty. In fact, in all these experiments, we did not use a length penalty because we did not have to. And why was that? Because we just tackled the heart of the issue. Now, one unfortunate thing is because the length degeneracy is largely gone, the translation quality measured by blue also go up even when we use a very large beam size for the beam search. However, we still, at least in terms of blue, we still get the best performing translations with a beam search with a very small beam size. Now, imposing or minimizing the oversmoothing loss does tend to increase the blue score, slightly, even when we use the beam search with the beam size 5, like the tiny bit, but that's really nothing compared to the gap between the translation quality of the translations generated from a beam search with a small beam versus translations generated from beam search with a large beam. What that means is that somehow problem seems to be to a certain degree solved. So we did indeed characterize the problem of oversmoothing, and we were able to come up with a solution that did indeed address this issue. But it doesn't look like we were able to address all the issues. It really, really works. Oversmoothing loss really works. It does reduce the oversmoothing rate, but somehow that doesn't lead to the improvements in the translation quality when we use very, very approximate search algorithm or the generation algorithm. That is beam search with a small beam size. So somehow there is a mysteriously unreasonable effectiveness of beam search with small beam that we cannot explain yet, even after this work and even after all the previous work that we have shown the various types of the degeneracies and proposed various fixes for them. So the mystery continues, even in this paradigm of neural order regressive models. And these are the mysteries that just need to be resolved, because these mysteries are not necessarily inherent to this paradigm of order regressive model, the statistical machine translation of the language model. So we'll have to fix it. I just don't know how to do it, but that's how research happens. We look at the problem, we see how people are solving it, we see what are missing, and then we try to characterize what those missing things are, and then we try to address those characterized missing things or the issues, one step at a time. Anyway, that actually concludes my lecture at this winter school. Thanks again for invitation. We're going to have an hour-long question answering, and I'll also be able to attend one of the poster sessions to talk with you, and then to try to answer any questions you have that I could answer, and also even ask you about your own research or your own study to get to know you better, and then for you to know me better as well. Well, thanks again for invitation, and thanks for listening to this long almost 2 hour long lecture, 2-part lecture, 2 hour long lecture on what doesn't work. That's a bit different from many of the other lectures, but I hope that this actually gives you the hope, pun intended, that this shows you that there are many problems that needs to be tackled. And it's not only about what we can do, what kind of more exciting stuff we do, but it's really all these gory details and then all these issues that we often just put it under the rug and then pretend that they don't exist are the things that require scientific pursuit. Well, thank you very much. I won't take up too much time of yours anymore. And then good luck. Enjoy the winter school. I'll talk to you later. Bye bye.